Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Stanford University School of Engineering. Vint Cerf and former Stanford President John Hennessy present evidence that contradicts foundational assumptions about networks and computation. Cerf describes a functional interplanetary internet operating since 2004 that inverts terrestrial protocols entirely. Hennessy reveals that in modern chips, retrieving data consumes 25 times more energy than performing calculations on it. These observations force a reconsideration of what we believe about connectivity physics and intelligence economics. Vint Cerf, one of the architects of the internet, delivers a claim that destabilizes our understanding of network engineering, the logic that powers the terrestrial internet. TCP, IP becomes completely non-functional the moment you leave Earth's atmosphere. On our planet, the fundamental assumption is immediate connectivity. If a data packet cannot find a route to its destination within milliseconds, the protocol discards it. The system treats the failure as a broken link and requests retransmission. This works because on Earth, connections are persistent and delays are measured in fractions of a second. Cerf identifies why this becomes catastrophic in space. Planetary rotation and orbital mechanics create communication blackouts lasting 20 minutes to several hours. Applying Earth's discard on delay logic would result in 100% data loss. The solution required inverting the core assumption of networking itself. They developed the bundle protocol, which operates on store and forward architecture. When a Martian node loses line of sight to a relay satellite, it does not drop packets. It stores them locally until a transmission window reopens. The network itself becomes a distributed storage system, transforming from a real-time flow into a custody chain. This represents a complete philosophical reversal. Connectivity is no longer assumed to be continuous. The physical infrastructure behind this network violates conventional engineering planning. We typically design purpose-built hardware for critical systems, dedicated satellites, specialized relays. Cerf reveals that the interplanetary backbone is constructed from repurposed scientific instruments. When spacecraft complete their primary research missions, instead of deactivating, they are converted into network nodes. The solar system internet is built from what would otherwise be abandoned hardware, turning expired science experiments into the foundational infrastructure of off-world communication. Cerf recounts a demonstration that exposes how packet-switched networks dissolve geographic logic entirely. They transmitted data from the Bay Area to USC, a straight-line distance of roughly 400 miles. Instead of direct routing, they sent it 88,000 miles through 2 synchronous satellite hops across the Atlantic, through multiple terrestrial networks, and back. The system functioned without degradation. The software remained indifferent to the detour. This proves that in packet-switched architecture, physical proximity has zero operational relevance. The geographic constraints that governed human communication for thousands of years have been structurally eliminated. John Hennessy introduces a hardware reality that contradicts our assumptions about computational cost. The prevailing belief is that artificial intelligence is bottlenecked by calculation complexity, the mathematical operations required for reasoning. Hennessy presents energy measurements that invert this model. Performing a floating point multiplication is cheap. Reading data from memory to perform that operation costs 25 times more energy. This creates a paradigm where computation is nearly free, but memory access is prohibitively expensive. The energy tax is not on thinking, it is on knowing. This physical constraint is forcing chip designers to regress to 1980s era systolic array architectures, where data only moves to adjacent processing units because the cost of moving information across a chip has become unsustainable. Hennessy highlights the ontological gap between biological and artificial intelligence through energy consumption. Current frontier AI models require gigawatt-scale data centers, power equivalent to entire cities, to perform training runs. The human brain, which executes general reasoning that no AI has replicated, operates on approximately 20 watts. That is the power draw of a dim light bulb. We are using millions of times more energy to achieve inferior results. This is not an incremental efficiency problem. It suggests our brute force approach to machine intelligence may be structurally flawed, ignoring principles that biology solved through evolution. Hennessy deflates the narrative around imminent artificial general intelligence by citing humanity's last exam, a benchmark containing 2,500 difficult reasoning problems. Current large language models score approximately 28% of failing grade by any academic standard. The distinction he draws is critical. Pattern recognition is not logical reasoning. We have constructed systems that excel at identifying correlations in vast datasets, but they remain primitive at the type of basic causal reasoning humans perform instinctively. Marty Hellman and Cerf introduced the concept they call the wisdom of foolishness, which challenges how we evaluate innovative ideas. The standard approach is to trust expert consensus and dismiss outlier proposals. Hellman and Cerf provide historical evidence that transformative technologies were systematically rejected by the very specialists paid to evaluate them. Packet switching, the foundation of the internet, was dismissed by defense establishment experts in the 1960s. Their reasoning was sound within existing paradigms. Networks required dedicated circuits, like telephone lines. Chopping data into independent packets was not just unconventional, it was considered fundamentally incorrect. GPS faced similar institutional rejection. The Air Force dismissed it because early receivers weighed 150 pounds and cost $250,000. Linear projection suggested the technology had no practical application. They could not foresee miniaturization curves that would compress that hardware into a $2 chip embedded in consumer phones. Cerf shares the story of early digital voice compression, where engineers reduced voice data from 64 kilobits per second to 1,800 bits. The audio quality was so degraded that every speaker sounded, in Cerf's description, like a drunken Norwegian. Standard telecommunications logic would classify this as failure. The military accepted it because connectivity mattered more than fidelity. They traded audio quality entirely for network functionality, violating every telecommunications standard of the era, but enabling the digital communication infrastructure we now depend on. These pioneers share a methodological consistency. They disregard socially constructed conventions and examine only physical constraints. Whether routing data through deep space to avoid packet loss or accepting unintelligible audio to maintain command networks, they operate on the principle that if something is physically possible, it will eventually become inevitable, regardless of whether it violates current regulations, economic models, or human intuition. The outstanding question is whether our existing mental frameworks for energy efficiency, spatial networking, and machine intelligence are capable of adapting to the realities these violations reveal. If you're interested in the video featured in this episode, click the link below to watch the original.